Softbodies are an extremely powerful way of creating cloth-like simulations, but without all the overhead and geometric limitations usually involved with physically accurate solutions, such as Maya's cloth plugin. Controlling softbodies, however, can sometimes be tricky. Basic techniques involving springs and a low goal weight work some of the time, but you're usually left with a simulation that's difficult, if not impossible, to control. Adding too much control by increasing your spring strength can sometimes result in spring tolerance errors, where your simulation breaks down into a garbled mess of particles, geometry, and springs. When viewed from a Zen perspective, gaining proper control over softbodies requires the user's realization that the user cannot control them. You need to find a balance in your simulation between absolute control and an acceptable level of dynamic randomness. Let's first look at some basic softbody examples so we can better understand how softbodies work. The generally accepted method for decreasing the amount of stretching in softbody simulations are to add springs and increase goal weight. Before applying either of these techniques, try reducing the conserve attribute on your particles to a value less than 1. Conserve is the amount of velocity your particles carry from one frame to the next. In the real world, there is always some sort of resistance to take into account, even in the vacuum of space, where gravitational pull from distant objects must be taken into consideration. I've found the wireframe spring creation method to be superior to the other two, min-max and all. However, each option still has its ideal uses. If you need to conserve the volume of a softbody object, the min-max method is essential, as you can set up an internal spring structure that spans one side of the object to the other. Quite often, I'll use multiple spring nodes on a single softbody object. This allows me to have iterative control over my simulation, from the smallest ripples to the biggest waves. In this example, the first spring node uses a wireframe walk length of 1 and has a very high stiffness and damping. This creates a strong relationship between all points and their immediate neighbors. I then create another spring object with a wireframe walk length of 2 with less stiffness and damping. I can then take it even further and create a third spring object with a walk length of 3 and even less stiffness and almost no damping at all. This technique works well for objects that don't need to preserve volume, such as curtains, sheets, flags, etc. If you need to preserve volume but not shape, use the same technique, but add an additional spring node created using the min-max method. Set your spring length so your springs are created from one side of the object to the other, not the surrounding points. You may need to execute this method several times with different settings, adding to the current spring object. This technique allows you to gradually decrease your min-max lengths until you have sufficient internal spring structure. Note that adding to existing springs created with wireframe walk lengths is not a good idea, as you want to control each of these objects individually rather than exert overall influence over your softbody. This file, called ch9 stretch resolution, demonstrates how different geometry resolutions will give different results. Here I have two planes, both made into softbodies with the outer row of CVs set to a goal weight of 1 and the rest set to a goal weight of 0. Both planes have springs created with a walk length of 2, which have identical stiffness and damping. The same gravity field is applied to both grids. The grid with 4x4 spans stretches 25% less than the grid with 8x8 spans. You could theoretically increase the stiffness of the springs on the high-resolution grid, add additional spring objects, or increase goal weight to achieve less stretching, but applying springs to lower-resolution objects usually results in better simulations. With lower-resolution softbodies, you have less overhead due to the smaller number of particles and springs required to solve the simulation. If you are creating a flag, curtains, or any type of fabric sheet, more points in your surface results in more stretching, as well as the increased chance of unwanted interpenetration. This file, called ch9 reduced mass, demonstrates how changing a softbody's mass attribute can affect the amount an object stretches. When you create springs, you can see the particle's mass attribute connected to the spring shape. The more particles you have in your softbody, the heavier it is, and the more the object will stretch under force. Reducing the mass of your softbody particles will result in less stretching overall. A good rule to follow is to figure out the combined weight of all your particles and divide that number by the particle count. I've done this in the runtime expression for both softbody grids. Here, I'm defining a total weight for my softbody with the $object weight variable. I've used a value of 100. I then divide that number by the total number of particles in the softbody, which I can get with the count attribute. This gives you a real-world number to work with, which helps achieve a more realistic simulation. Remember, the more accurate you want your simulation to be, the more time you should spend setting up each variable to behave properly. Try to use real-world information relative to the effect you are simulating, and you'll achieve real-world results. Let's look at a real shot which involves softbodies. When working with softbody dynamics, I prefer to balance control by using a blend shape to toggle between keyframed motion and dynamic simulation. In the softbody technique that follows, you'll learn how to spread control over multiple deformed objects, be they blend shapes or nonlinear deformers. This technique allows you to greater control over the final result, as you are able to simply dial in and out the amounts of dynamics you want. The key to this technique is the ordering of your deformations and the hierarchy above your softbody object. I've opened the file ch9 Banshee Base in the Scenes directory of my project directory. The animation's 211 frames long. If I play through the entire frame range, you can see a character with straps trailing behind. These straps will be the focus of this project. I need to have the straps flowing dynamically behind the character as it flies through the air. There are several techniques we could implement to create this dynamic motion. In this example, we're going to use a combination of joints, IK splines, softbodies, and springs. The advantages of this technique afford me a wide range of motion by way of simple high-level controls, as well as minimal stretching problems due to the fact that these joints won't stretch. Let's focus on the strap hanging off the character's head. I'll start by building a joint chain down the length of the bandage. 6 to 10 bones should be enough to give me a smooth, flowing deformation. An easy way to create bones along this surface is to snap to its control vertices. Next, I'll bind this surface to these joints using Smooth Bind. In the Smooth Bind option box, I'm going to set my bind method to closest distance and my max influences to 2. I'm using a distance-based approach so I have better control of the fall-off between joints. I've specified to use a maximum of 2 influence joints, as using more than this would result in too smooth of a bend, more of a bowing action. To control these joints, I'm going to use an IK spline handle. Rather than have this tool automatically create a curve, however, I'm going to create my own. I'm doing this because the automatically generated curve will give me too many CVs. Additionally, the Auto Simplify Curve option of the IK Spline tool results in too few CVs. An easy way to create my own curve is to duplicate the center isoparm of my original surface. I'll then rebuild it to 6 spans, which will give me the correct amount of detail. I'm going to rename this curve to Head Spline CRV. I'll now use this curve as an IK spline handle for my joint hierarchy. Next, I'll make this curve a softbody. I'm going to set my creation options to duplicate Make Original Soft, turn on Make Non-Soft a goal, and make sure the weight is set to 1. My original curve is now a softbody that controls my joints, and I have a duplicate curve that the softbody is goaled to. I can now use the goal curve in conjunction with the softbody's goal PP attribute to control the balance between dynamics and keyframed animation. I'll rename my duplicate curve to Head Spline Goal CRV and parent it under the head geometry of the character so it follows along. All my CVs have a goal weight of 1, causing the strap to look rigid and non-dynamic. I want the tail end of the geometry to flap in the wind behind the character, which means I need a high goal weight for the first 2 CVs particles near the head, and a gradually decreasing goal value as the particles get further away. I could select each particle and assign a weight to it in the component editor, but that can be quite tedious and time-consuming if I need to make changes later on. Instead, I'll use a combination of runtime expressions, custom attributes, and a ramp, which will provide me with a visual indicator of the softbody's goal weight. I'm going to add 2 per particle float attributes to my softbody called GoalRamp VPP and GoalRamp PP. I'll also create a per object float attribute called GoalLock. Fortunately, these softbody particles are sequentially ordered from first to last, first being closest to the character's head. This means I can use my particle ID attribute as a way to look up a value in a black to white ramp. I first need to normalize the IDs so they're remapped to all lie between 0 and 1. I'll do this in my runtime expression. If I change the particles to numeric display mode and show values for goal ramp VPP, you'll see the values distributed between 0 and 1. I need to pipe a ramp's output into the particle's goal ramp PP attribute. I'll do this in the particle's attribute editor by right mouse button clicking on the goal ramp PP field, navigating to Create Ramp, and select the option box. I'll tell the ramp's input V to read the per particle attribute goal ramp VPP, which you'll recall had normalized values from 0 to 1 assigned to it. You'll notice as soon as this is done, the numeric display of goal PP in the viewport changes to show numbers between 0 and 1. If I tweak the ramp's values, I can indirectly change the goal PP amount on each particle. I'll add some gravity to the softbody particles and turn their conserve attribute down to 0.95. It's important to always reduce your conserve attribute from the default value of 1. Most of the time, you'll want your particles to lose a bit of their energy as they move around. Otherwise, you'll spend most of your time trying to chase them down with various fields to control their movement. I've found that conserve values in the range of 0.9 to 0.985 work well for most simulations. You can see during playback that my softbody curve is now trailing behind the character. Note the lack of stretching in the strap as the IK spline handle doesn't stretch the bones. The softbody curve itself is stretching too much, causing the bones to follow a very straight path. I'm going to add some springs to the softbody particles. Doing this will not only keep the curve together, but it will also add dynamic feedback to the entire curve by transferring energy from one particle to the next. I'm going to create two spring objects. The first will have a wire walk length of 1 and a stiffness of 75. The other will have a wire walk length of 2 and a stiffness of 15. Using this layered approach gives me general and specific control over these springs at the same time. While the particles still stretch, it is to a much lesser extent than without springs. If desired, I could tweak the spring stiffness values to further minimize stretching. Now that we've created our dynamic motion, we can start adding high-level controls which will allow us to make very precise changes to the strap's performance. I'll start by utilizing the goal lock attribute on my softbody particles in conjunction with deformations and a blend shape. I'll first have to clamp the goal PP in my runtime expression to a maximum value of 1. Otherwise, the softbody dynamics will get unpredictable. I can then add the goal lock attribute to my goal ramp PP attribute. I can now overdrive my goal values easily with my goal lock attribute, thereby offsetting my particle's goal PP attribute. This will allow me to globally add or remove dynamic influence over the entire softbody, should I require more or less control over the particles. I'll set goal lock to a value of 0.25 to stiffen up the softbody. Another advantage of goal lock lies in its ability to be keyframed. Setting your goal lock to 1, you are able to move your character to a different position, then keyframe it down to a lower number a few frames later. This lets you avoid having to perform a dynamic run-up to let your softbodies catch up with your scene. All this would be quite time-consuming if you were dealing with goal PP on its own. As an added bonus, you maintain the goal relationship between all your particles no matter what you set goal lock to. Next, I'll duplicate the goal curve to use as a blend shape onto itself. I'll rename this resulting curve to Head Spline Deformation CRV. I can now use this deformation curve as a blend shape target for the goal curve. I'll first select the deformation curve, then the goal curve, and select the menu item Deform, Create Blend Shape. This allows me to apply deformations to the goal curve so that when my goal lock is set to 1, the softbody will conform to the deforming curve, as all the particles' goal PP will be set to 1. When goal lock is 0, the particles will follow the original curve using a combination of dynamics and goal PP. I now have balanced control between dynamics and keyframed animation. I could go ahead and make multiple blend shape targets for the goal curve, some controlled by clusters, some by nonlinear deformers such as wave or twist. For example, I've added a bend deformer to the blend shape target in this scene. Using a ramp to control the goal PP distribution along my curve proves to be a nice, quick way to control the weighting between points on my particle object. If I wanted these straps to stretch, however, I could have simply skipped creating the joints and created a wire deformer out of my deformation curve. As a finishing touch, I'll add turbulence and wind to this strap so it appears to flap randomly as if influenced by air rushing by. Because the character changes direction, however, adding wind will not be trivial. I could add an airfield and calculate the character's velocity per frame. However, this would involve a relatively slow expression that would have to query a particle's velocity every frame using the particle command. One thing I always try and avoid is crossing expressions over from the scene universe to the particle universe. Maya uses different engines to calculate regular expressions and particle expressions, and using the regular engine to query a per particle attribute can slow down your scene's playback. Looking at my animation, I notice that the first particle in my softbody curve never moves in relation to the character's head. This is because that particular particle always has a goal PP value of 1. I can query that particle's velocity attribute and create my own wind force, which will influence all particles in my softbody. I'll create a per-object attribute on my softbody particles called wind speed. I can then modify my runtime expression to calculate wind direction. I only calculate the vector $wind_v inside my if loop because I only want the velocity from the first particle. I first normalize the vector using the unit function, which returns a vector with a length of 1. Then I multiply the result by the wind speed attribute. Because the velocity vector points in the direction of travel, I have to invert the vector by multiplying it by -1, so the wind will blow in the opposite direction of the character's movement. Finally, I'll add this value to my existing velocity. This fake airfield should smooth out most of the high-frequency turbulence I've added. To make sure it's working, I'm going to turn off goal lock so my softbody can move freely. Now, when I play the scene and increase the particle's wind speed attribute, I can see how the wind affects the softbody's movement. It's necessary to find a balance between goal lock and wind speed, as too high a wind speed will stretch the springs too much. I seem to get nice results with a goal lock of 0.25. I can now even animate the wind speed to change throughout the sequence.